Section 5.1 is nth roots and rational exponents. And a lot of the times when we have rational exponents, it's easier for us to simplify them or evaluate them when we rewrite them as radicals. So a rational exponent just means that you have a fraction exponent. So we'll say we have like b raised to the e over r. So numerator is e, denominator is r. And then how we change that to a radical is the b goes inside the radical, the r becomes our root, or like it's called an index, and the e becomes the exponent outside of the radical, or it could even be inside the radical. That's kind of interchangeable. So for example 1, number 1, it's 25 to the 3/2 power. So I can rewrite this in radical form, and then it's going to be a little bit easier to simplify. So my base is, or my b is 25. So b is going to go, or sorry, 25 is going to go inside the radical. And then the denominator of my fraction is r. In this case it's 2, so it's going to be a second root, or a square root. And then the numerator of the radical, or the numerator of the rational exponent is e, and that becomes our exponent, so our exponent is 3. So this means we have to take the square root of 25 and then raise it to the 3rd power. So the square root of 25 is 5, and then 5 cubed is 5 times 5 times 5, so that's 25, or 125. And then for number 2, it's 16 to the negative 5/4, so we'll do the same thing. B is 16, E is negative 5, R is 4. So if I want to rewrite this in radical form, the 16 goes inside the radical. My root is 4. And then I'm raising that to the negative 5th power. So the 4th root of 16, that means what number times itself 4 times equals 16? It would be 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So the 4th root of 16 is 2. And then I'm raising that to the negative 5th power. Properties of negative exponents tell us that we have to, if we have a negative exponent, we need to take the reciprocal of the base. So in this case, my base is 2. So 2 to the negative 5th is going to be the same thing as 1 over 2 to the 5th. And then 2 to the 5th is 32. So this becomes 1 over 32. And then for number 3, 81 to the 3/4. So 81 is my B, 3 is my E, 4 is my R. So it would be 81 inside the radical. And then 4 becomes my root, or my index. And I'm raising that to the 3rd power. So the 4th root of 81 is a number times itself 4 times. So if we do 3 times 3, that's 9. Times another 3 is 27. Times the 4th 3 is 81. So the 4th root of 81 is 3. And then we have to raise 3 to the 3rd power. So 3 to the 3rd power is 3 multiplied 3 times. So that's 27. And then 9 to the negative 1/2. So 9 is my base, negative 1 is my exponent, 2 is my root. So it's the square root of 9 raised to the negative 1 power. And then the square root of 9 is 3 to the negative 1. And since I have a negative exponent, I need to take the reciprocal of the base, which in this case is 3. So 3 to the negative 1 is 1/3. So anytime you have a rational exponent, you should reorder it, or you should rearrange it into a radical to make it easier to simplify using this little, I don't know, strategy up here. I would write this on the top of your homework though to make it easier. And then for example 2, it just says solve. So if we look at the first one, it's 5x cubed minus 320 equals 0. So we just have this one term with an x. In this case, it's x cubed. So we're going to solve it like we would if we were solving by square roots, where we want to isolate what's being cubed now. and then eventually we'll end up cube rooting both sides. So if I want to isolate the x cubed, I'm going to add 320 to both sides. So then this cancels out. I'm left with 5x cubed equals 320. And then I'm still isolating the x cubed, so I can divide both sides by 5. So the 5's cancel out. And then I'm left with x cubed equals 320 divided by 5 is 64. So I can cube root both sides to cancel out the cubed and isolate x completely. So the cubed root of 64, I'm looking for a number multiplied by itself 3 times that equals 64. So 4 times 4 is 16, and then times another 4 is 64. So the cubed root of 64 is 4. So our solution is x equals 4. And then for number 2, it's x plus 3 to the 4th equals 24. So now what's being raised to the 4th power is already like isolated. There's nothing added after it or multiplied before it. So if I want to get rid of like the 4th power, I can just go ahead and I can 4th root both sides now to cancel out the 4th power. So the 4th root cancels out the 4th power, and I'm left with x plus 3 equals the 4th root of 24. And then in order for us to figure out, eventually we'll subtract the 3 over, but we have to think about if this 4th root of 24 can be simplified. So usually when we simplify radicals, we think like, is there a perfect square factor when it's like just a square root? So now since it's a 4th root, we have to think, is there like a perfect 4th factor? So the smallest like perfect 4th factor would be 2 to the 4th. So 2 times 2 is 4, and then times 2 is 18, times 2 again is 16. So the smallest like perfect 4th factor would be 16, and then the next one is like 81 because it's 3 to the 4th. So like the 4th root of 24 cannot be simplified at all. But whenever you have a even root, you need to include the positive or negative answer, because even if like the 4th root of 24 is a decimal, it's going to be either the positive decimal or the negative decimal. So yeah, the 4th root of 24 is like 2.21 something something something, but it can also be negative 2.1 something something something, because a negative times a negative times a negative times a negative would get us a positive. So if you have an even amount of negatives together, you end up with a positive. And then the last thing is we can subtract the 3 over. So we have x equals negative 3, and then plus or minus the 4th root of 24. So x equals negative 3 plus or minus the 4th root of 24. So anytime you have an answer that has a 4th or an even root in it, you have to include the positive or negative answer. You don't need to do it for an odd root though. So we don't need to do it here, for example, because like negative 4 to the 3rd power isn't positive 64. It's negative 64. So it would be negative 4 times negative 4, which is 16, and then times another negative would end up being negative 64. So even roots, yes, plus and minus. Odd roots, no. And then for number 3, 1/2 x to the 5th equals 512. So same thing, we want to isolate now what's being raised to the 5th power. So I want to get rid of that 1/2. So to get rid of that 1/2, I can multiply both sides by 2. So then these cancel out. I'm left with x to the 5th equals 512 times 2, which is 1024. And then from there, I need to 5th root both sides. So 5th root both sides. And then if you're not sure if something like has a 5th root to it, you can honestly plug it into the calculator to see if it is a 5th root, or if you can simplify, like in order to simplify it, if it's not a 5th root, you might have to make a factor tree. So I'll show you how to do the factor tree because it'll work for both. So 1024, whenever I do factor trees, this might not be enough space. I usually just start with dividing by like 2 or 3, like if it's odd or even. So So 1024, if I divide it by 2, I get 512. And then 512, if I divide it by 2, I think it's 256. Yeah, 2 times 256. And then 256 divided by 2 is 128. And then 128 divided by 2 is 64. 64 divided by 2 is 2 and 32. 32 divided by 2 is 2 and 16. Still ran out of space. 16 divided by 2 is 8 and 2. And then 8 divided by 2 breaks down into 4 and 2, and then 4 becomes 2 and 2. Okay, so now we have all of our primes finally. So if we have, we'll count how many 2's we have because everything broke down to a 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So anytime we're taking the 5th root of something, we just need like 5 of the same number. So there's like 1, 2, 3, 4, 5 2's right here. So we can at least pull out a 2 out of that radical. And then there's 1, 2, 3, 4, 5 right here. So we can actually pull out 2 2's. So we can pull out 2 times 2. So that means that the 5th root of 1024 is 4. So x equals, we'll pull out 2, we pull out another 2, so 2 times 2 is 4. And then again, because it's a odd root, it's just positive 4, not negative 4 also. So that's it for 5.1. We combined 5.1 and 5.2 into the same lesson. So 5.2 is properties of rational exponents and radicals. So this goes back to, or this kind of like builds off the properties you learned in Algebra 1. If you don't like quite remember them, I would really recommend spending a little bit of time reviewing them because it'll just make your life a lot easier. So example 1, properties of exponents. So our first one is 13 to the 1/3 times 13 to the 1/6. So when we have the same base, and our base is 13 in this case, our exponent is 1/3 and 1/6, but our base is 13. When we have the same base and we're multiplying, we add the exponents. So this would be 13 to the 1/3 plus 1/6. And then once we add those exponents, we have our simplified answer. But in order to add the fractions, we have to have common denominators. So I'm going to change 1/3 to 2/6. And then I have 13 raised to the 2/6 plus 1/6, so that's 13 to the 3/6. And then 3/6 obviously can reduce down to 1/2, so 13 to the 1/2 power. And then for number 2, we have 5 to the 1/5 times 8 to the 1/4, all raised to the 5th power. So now in this case, like our base isn't the same. One base is an 8 and one base is a 5. So we can't add their exponents or anything. We can't combine those. But when we have multiple like factors inside, or different things that are being multiplied together and they're all being raised to the same power, we can kind of like distribute that power in. So this doesn't work for different terms, where if you're like adding them, it wouldn't work. But if you're multiplying the 2 different things or 3 different things, however many different things you have, you can kind of distribute the 5th power to both of these. So when you raise a power to a power, you multiply those exponents. So this would be 5 to the 1/5 times 5, and then times 8 to the 1/4 times 5. And then 5 to the, so 1/5 times 5 is just 1. So this is just 5 to the 1st power times 8 to the 1/4 times 5. 1/4 times 5 is 5/4. So times 8 to the 5/4. So it looks too big. So 5 times 8 to the 5/4. And then for number 3, it's 8 over 8 to the 1/9. So when we have the same base, like we have an 8 and an 8 right here, when we have the same base and we're dividing, we subtract their exponents. So this is 8 to the first power, but we can think of it as like 8 to the 9 ninths because we'll need common denominators. So we have the same base, we're dividing, so we're going to subtract their exponents. It's going to be the top exponent minus the bottom exponent. So it's 8 to the 9 ninths minus 1 ninth. And then 9 ninths minus 1 ninth is 8 ninths. So it's 8 to the 8 ninths. And then I know I said like we're going to subtract like the top exponent minus the bottom exponent. You can do like the other way. If say like the bottom exponent is smaller, you would just leave your final answer in the denominator and the numerator would become 1 if that was the case. So the next section is all about simplifying radicals. So especially when things are like not just square roots, we'll have to really think on how to simplify them. So for number 1, it's the cubed root of 500. So we have to think like, is there a perfect cube factor of 500? So and if you're not sure, like as we go through this section, you're going to start to get more like familiar with certain like numbers, like perfect cubes, perfect like fourths, kind of like you did with perfect squares. Like I don't know when we first learned them, but earlier on, like the whole like 4, 9, 16, 25, all those, we'll start kind of familiarizing ourselves with perfect cubes, but we can just kind of go through and like figure some of them out. So like 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, that one will pop up a lot, 6 cubed is 216. So start kind of familiarizing yourself with those numbers. So are there any perfect square factors of, or sorry, perfect cube factors of 500? So 125 is a factor of 500. So 500 divided by 125 is 4. So since 500 divided by 125 is 4, I can break this radical down into the cubed root of 125 times the cubed root of 4. And then the cubed root of 125 we know is 5. So the cubed root of 125 is 5 times the cubed root of 4. We obviously can't simplify the cubed root of 4 at all, so we're done there. You can also do the same thing. You can always make a factor tree for something like this if you're not sure, if you don't have a calculator. So like for 500, I know 500 is divisible by 5. So we do 5 times 100. And then I know like 100 is divisible by 5 also. So 5 times 20. And then I know 20 is divisible by 5 also. So 20 divided by 5 is 5. And then I have a 4 left over. So since I am finding the cubed root, I'm looking for 3 of the same number so that I can pull out. So I have 3 5s. So that means that I can pull out a 5 from this radical, and I'm left with the 4 inside the radical. So the 5 comes out because I have 3 5s. That means I can take the cubed root of those, pull the 5 out times the cubed root of 4 because that was left over. For number 2, so it's the 5th root of 3/4. Whenever we have like a fraction inside the radical, we can separate like into 2 different radicals, numerator and denominator. So I can think of this as the 5th root of 3 over the 5th root of 4. And then usually when we have a radical in the denominator, we like rationalize the denominator, but it's a little bit different when it's like not a square root. When it's a 5th root or a cubed root or any root other than squared, it's a little bit different. So if it isn't a square root, what we want to do is we want to first, if like 4 can be rewritten as a power, we want to do that. So like a prime raised to an exponent. So I can rewrite the 5th root of 4 as the 5th root of 2 squared. So I'm not changing the value at all, I'm just changing 4 to 2 squared. And then there's still the 5th root of 3 in the numerator. So usually when we rationalize the denominator, we multiply numerator and denominator by like the radical in the denominator to cancel it out. So I need to multiply numerator and denominator by something that gets me to the 5th power in the denominator. So right now I have the fifth power, or the fifth root of 2 squared. So since I have 2 squared, I'm going to multiply in a 2 cubed, or the fifth root of 2 cubed, by numerator and denominator. And the reason I'm multiplying in a 2 cubed is because I want this 2 squared to become a 2 to the 5th power, because anything that where the exponent matches the root, they just like cancel each other out. So in the denominator, I'm going to end up with the 5th power of 2 squared times 2 cubed. I add their exponents because the bases are the same when we're multiplying. So 2 squared times 2 cubed becomes 2 to the 5th, and we can just multiply it all under one radical because they're the same root. And then up here, I can still multiply within one radical because it's still the 5th root and the 5th root. So it's going to be the 5th root of 3 times 2 cubed. So that's like 3 times 24, or sorry, 3 times 8. So 3 times 8 is 24. Sorry if that was confusing. 2 cubed is 8, so we're just multiplying 3 times 8 to get 24. And then now we're able to like actually cancel out the radical in the denominator, which is what we were going for. Because anytime I have like a 5th root and a 5th power, those like undo each other. They're basically inverse operations. So anytime the root matches the exponent, they cancel each other out. So we're just left with 5, or the 5th root of 24 over 2. And then we can't simplify the 5th root of 24 at all, because I think the smallest 5th root is 32. So just the 5th root of 24 over 2. And then for number 3, it's 1 over root 7 minus 2. So whenever you have, like, when we just have a radical in the denominator, usually it's easy, we just multiply by another radical to cancel it out. But when you have a radical and another term, you have to use kind of like the difference of squares pattern in order to cancel it out. So like we know like a difference of squares is a squared minus b squared, and then that factors into a plus b times a minus b. So the reason that like this itself, when we FOIL it back, it goes back to 2 terms instead of 3 terms, is because these terms are the same except for one is a plus and one is a minus. So we're going to use that pattern in order to get rid of the radical in the denominator. So if you have multiple terms, or if you have 2 terms in the denominator and one is a radical, you have to multiply numerator and denominator by the same numbers, but you're going to flip the sign. So we're going to multiply numerator and denominator by root 7 plus 2 instead of root 7 minus 2. And the reason is because we're going to FOIL this, basically. We're going to FOIL the root 7 minus 2 times root 7 plus 2, and the radicals are going to cancel out. So in the numerator, I'm just multiplying 1 times root 7 plus 2, so that just stays root 7 plus 2. And then in the denominator, if I were to FOIL this, so root 7 times root 7, that's just 7. It's like the square root of 49, so 7. And then root 7 times 2, so that becomes plus 2 root 7. And then we have negative 2 times root 7, so that's negative 2 root 7. And then negative 2 times 2 is negative 4. But then the positive 2 root 7 and the negative 2 root 7 cancel out. So we're just left with root 7 plus 2 in the numerator over 7 minus 4 in the denominator. So 3. So 7 minus 4 leaves us with 3. So root 7 plus 2 over 3. And then notice, like I said, we're using the difference of squares pattern, which, like, I don't know why I erased it, but we know that when we multiply the difference of squares, it multiplies back into a squared minus b squared. And the same thing happens here. So like if this is a and b, we ended up with a squared, which was 7, and then b squared, which was 4. So a squared minus b squared end up being 7 minus 4. So it's that same pattern. And then for number 4, it's the 4th root of 84 minus the 4th root of 3. So they're both 4th roots right now, but like when you're just subtracting, you can't actually like subtract them even if they're the same, or adding or subtracting. You can't do that even if they're the same root. We need them to have like the exact same number inside of the radical in order to subtract them. So I'm going to have to try to simplify the 4th root of 84. The 4th root of 3 can't be simplified, but I'm going to try to simplify the 4th root of 84. So I'm going to make a factor tree. So I know 84 is divisible by 2, and then that's 2 and 24. And then 24 is divisible by 2, 2 and 12. And then 12 breaks down into 2 and 6. And then 6 breaks down into 2 and 3. So we have 4 of the same number. We have 4 2s, and then there's a 3 left over. So if there's 4 of the same number and it's a 4th root, I can pull out that number. So I can pull out a 2, and then I'm left with the 4th root of 3, because there was a 3 also in the factor tree. And then minus the 4th root of 3. And now this is basically like combining like terms. So this is like 1 times the 4th root of 3. So if I have 2 times the 4th root of 3 minus 1 times the 4th root of 3, it's almost like 2x minus x. So you just subtract the coefficients, the 2 and the 1. So 2 times the 4th root of 3 minus 1 times the 4th root of 3 is just the 4th root of 3. It's just 1 times the 4th root of 3. So in order for us to add or subtract, like even if it's the same root on the radical, you have to have the number inside the radical be exactly the same, and then you just add or subtract the number in front, the coefficients. And then for number 5, it's the same kind of idea. So we have the cubed root of 5 plus the cubed root of 40. So the root is the same, but like what's inside the radical is not. So we'll have to try to manipulate it to get it to be the same. So we'll make a factor tree for 40 and see if we can change it the same way. So for 40, I know I can divide by 2. It'd be 2 and 20. And then 20 breaks down into 2 and 10. 10 breaks down into 2 and 5. So we're taking the cubed root, so we're looking for 3 of the same number. I have 3 2s, so I can pull the 2 out, and then I'm left with the 5 inside the radical. So it'll be 3, or the cubed root of 5, that stays the same. And then plus the cubed root of 40 simplifies to 2, because I had 3 2s, so I can pull out a 2, times the cubed root of 5, because I also had a 5 in the factor tree. And then now it's just like adding 1 times the cubed root of 5 plus 2 times the cubed root of 5. So altogether 1 plus 2 is 3, and then times the cubed root of 5. So same thing here, like as soon as we get the same number inside the radical, we're able to add and subtract, but we just change like the coefficient. We just add or subtract the coefficients. And then for number 6, it's the cubed root of 2a to the 13th, b cubed, and then c to the 8th. So there's a couple of different ways that like you can approach this. You can divide, or I'll show you both ways. So sorry. So one way is to kind of break down values, like, or break down the exponents inside the radical into things that we can like take the cubed root of. And basically like when you have a number or an exponent inside the radical and you want to take the cubed root or whatever root, we're dividing like these exponents by the root. So like we'd be dividing 3 by 13 and divide 3 by 3 and divide 8 by 3. So if you go to the division route, you're just gonna, the remainder is gonna stay inside the radical, or we can kind of do that work ahead of time and break down our exponents. So the 2 will stay there, that's just to the first power. If I want to break down like a to the 13th into something that's divisible by 3, I can break it down into a to the 12th times a, and then b cubed, that's already divisible by 3, so we're good there. And then c to the 8th, I can break down into c to the 6th times c squared. So like where the same amount of c's being multiplied together, it's just I wanted to break down into c to the 6 because it's divisible by 3. And then now I can start pulling things out. So in order to pull things out, it's like divisible by our root by 3. So the 2 has to stay in. The a to the 12th I can pull out by dividing 12 by 3. So it'd become a to the 4th. And then an a stays in there. Just make sure you're like paying attention to what stays in there. So far we have the 2 and the a. B cubed, I could divide the 3 by 3. So b to the 1st power comes out because 3 divided by 3 is 1. And then c to the 6th, I can pull out a c squared since 6 divided by 3 is 2. And then that c squared stays inside. So left over I had a 2, and then I had the a, and then I had the c squared left over inside. So a to the 4th b c squared times root 2a c squared, or the 3rd root of 2a c squared. And then the other way of looking at it is if like you don't want to break down the numbers like this, you can do it all in one step. You just have to make sure that like you're dividing and like figuring out the right remainder. So like 2 is just the 1st power. I can't take the cubed root of 2, so that stays inside the radical. And then a to the 13th, if I divide 13 by 3, I get 4, and then but there's 1 left over. So I can pull out an a to the 4th with an a to the 1st power left inside the radical. And then b cubed, I could divide 3 by 3 with nothing left over, so I just get to pull out the b to the 1st power with no b's left over inside the radical. And then for c to the 8th, I can divide 8 by 3, it's 2, but then there's 2 left over, so c squared has to come out, or has to stay in the radical also. So a to the 4th bc squared times the cubed root of 2ac squared. And then for 13, so it's x squared over the cubed root of 13. So the first thing I can do is I can at least simplify, or I can at least take the cubed root of part of that y to the 13th. I think I said a, but I meant y. So the x squared is going to stay in the numerator. Nothing changes there. And then I'm going to break down like the y to the 13th into something that I can take the cubed root of. So y, or the cubed root of y to the 12th times y. Just like the closest thing that's divisible by 3 that's less than 13 is what I was looking for. So the x cubed, or the x squared, will stay in the numerator. And then the cubed root of y to the 12th, I just have to divide 12 by 3, so that's y to the 4th. And then I'm left with the cubed root of y. So I have to figure out a way to get the radical out of the denominator. So right now I have the cubed root of y. The next closest thing that I would be able to take the cubed root of would be y cubed. So I'm going to multiply in a y squared, because I already have y to the 1st power. So I'm going to multiply numerator and denominator by y squared. So multiply numerator and denominator by the cubed root of y squared. And then the numerator becomes x squared times the cubed root of y squared. And then the denominator becomes y to the 4th. And then the cubed root of y to the 1st times the cubed root of y squared. That becomes the cubed root of y cubed, which is what we wanted. All we did, that's why we multiplied in the y squared, was to get the y to the 1st power times y squared to become y cubed, so that these could cancel each other out. So then now these do cancel each other out, and this just becomes y to the 1st power. So the numerator, I'm left with x squared times the cubed root of y squared, and then that's all over y to the 4th times y, so y to the 5th.